Hey folks, we're back again. I'm Derek,
I'm Paul.
and this is part 3 of our mini-series on precipitator assessments. So today we're going to talk about voltage, and Mr. Precipitator will explain that to you.
Yeah, I'll go over to the grease board again. I got the same drawing of the precipitator over there. This is our three-part. I tried to break this into 3 parts. In the first one, we just talked about the physical size of the precipitator. Second one is about wrapping. The third one's power supplies. This is going to be the longest video of the 3, just because it takes a little bit to explain it. But it's actually the most important part. If you can't get the right voltage in the precipitator, it just won't run right. So I'll take you over there and I'll explain it to you. So when it comes to voltage and current in the precipitator, precipitators aren't quite as intuitive as motors or things of that sort. So I'm going to talk about this a little bit. The most important part is going to be what's called particle migration velocity, and that's the speed in which the particulate that we're trying to remove moves out of the gas stream and migrates over to the collecting plate. That is the most important function of a precipitator. So if you look at the equation, you have migration velocity here, you have the diameter of the particle, and you have voltage twice. You have the charging voltage and the collecting voltage. Now underneath it is just 4 pi viscosity of the gas. If you notice, there is no current in this equation. The current is the result of applying the voltage. Voltage is force, current is electron flow. So it's in there twice. So for every increase you can do in voltage in a precipitator field, you will square the collection efficiency of the particle. So voltage is very important. So we'll come back over here to a VI curve. As you increase in voltage, we have kV down here on the bottom. I didn't write that in there, I'll do it now. And milliamps along the y-axis. So as we increase in voltage, we're going to draw more current from the transformer. And it's different between a wire or a rigid discharge electrode. A wire has a little bit flatter line, and the RDE has a sharper VI curve. What happens here is sometimes you will change your wires to a rigid discharge electrode, which you stop the failures of these wires because RDEs are virtually indestructible. But you moved your VI curve. So if you didn't update your TR sets at that time, you may not have enough ampacity. So as you get up here to say 50, 60 kV, your current was X with the wires. Now, if that's your TR set limit, this is your limit for voltage. So you're limiting your voltage only down to 30 kV. Same current, but if you go down here, voltage is in here twice. So if you reduce voltage, your particulate collection efficiency goes way down real quick. So, when you're assessing your precipitator, what you need to see is not how much current, it's how much current you have available for those TR sets. Can you ramp all the way up on your VI curve? And this is a real simple thing. You take your collecting area again, where we talked about this earlier, where you have your height, length, times 2. There's 2 sides of the collecting plate, number of collecting plates. Once you have your area, you can determine your current density. So we have microamps per square foot. In your inlet, it's going to be the lowest. Your outlet's going to be the highest. And that's because of particulate loading. It also has a lot to do with the diameter of the particle. Your larger diameter particles are going to get collected early on, and it's your fine particulate at the end that is really causing the high opacity, but it's your final particulate at the end that takes the most amount of current availability. So, and these are rule of thumbs based on your type of discharge electrode has a lot to do with it. But your inlet fields may be 10 to 20 microamps per square foot. Sorry for my bad writing. Your outlet field could be as high as 100 plus microamps per square foot. So one of the things when you're assessing is, do I have enough ampacity for this field? I had an earlier video where I talked about where they did go from a weighted wire design to a rigid discharge electrode design, kept the same TR sets, and now they're plagued with current limit on every field, and they're not able to get their voltage up. But typically when you look at a precipitator, you're going to have your highest kV on the inlets and the lowest milliamp. That doesn't mean it's not performing. You have low current. A lot of people interpret low current means, oh, low load. Like a motor, if it draws less current, it's not turning as fast or don't have as much torque to it. On a precipitator, it's different. Your voltage is the highest. So you have the most amount of force because there's so much particulate in that field, you're not getting a lot of electron flow. But you'll still collect 80 to 90% as far as mass weight of particulate on your inlet fields. The second field, or then your outlet field, you're going to have your lowest kV because there's not much particulate in there, so it don't take a lot of force to move it over to the plate for the electrons to flow, but you'll have a lot of electron flowing, so you'll have the highest current. So typically you're spark limited on your inlet fields, or you should be if your TR sets are properly sized. You'll have your highest kV, lowest milliamp. Somewhere in the middle, you'll stop sparking and you'll get more to a current limit. By the time you get to the outlet, you'll have your lowest kV, highest milliamp, and you should always be a current limit on your outlet field. Now, you get to the point where you can't put enough ampacity on there because what happens is your VI curve at some point will just go straight up. So you can keep adding current all you want, you're not going to get any more voltage out of it. So these are areas that you got to look for, and this is where the assessment comes a little more tricky. So I hope I answered some of your questions, and if you have any more, please call me, and that's basically it here.
Well, there you have it, folks. That concludes our three-part series on precipitator assessments. We will have a follow-up video with an overview, and Paul will explain a little more about that.
Yeah, so we'll wrap it all up so you can assess your precipitator, and we'll give it a grade. I like going simple where it's green, yellow, or red. Red, you're just not big enough. Where green, your precipitator is large enough. It's just an underachiever. A lot of times when you get a green assessment and you have high opacity, it's pretty easy to fix. It's just low-hanging fruit that you got to take care of. But we'll get into that a little bit later. For now, I hope you enjoyed this one, and stay safe.
Be well.